I'm going to tell you a little bit about what we do. So Bell Labs, crazy place. Just a question, how many of you think Bell Labs is dead? Because it would be disappointing. So Bell Labs isn't dead. Bell Labs is 90 years old, and what's the role of Bell Labs is what it's always been, actually, which is to invent the future. All that's changed is the scope of that future, but the mission is the same. It started about 90 years ago. It's invented lots of stuff. It's invented the transistor, cellular communications, Unix, C++, solar cells, optical communications. Pretty much everything you use today when we communicate with these things is actually sort of communicating with components and over networks that Bell Labs invented, and even operating system. All of Linux, of course, is derived from early versions of Unix. So you may think, well, where's it been? Where's Bell Labs been? Well, it's actually been inventing away, but we've been in an era that's been a bit different. I'm going to talk about that era. That era has been one where software and services have dominated, probably. Web services in particular, and the internet as a set of web platforms has been the dominant thing that we've been experiencing as human beings. And what I'm going to argue is we're about to enter an era where, in fact, we're going to build new infrastructure. So if you think about what Bell Labs did in the past, build the infrastructure of the past, and I would argue of the present, of course, but we've got to actually rebuild that infrastructure in order to digitize our world. And that's what we've been working on. And so I'm going to tell you a bit about that. Not deeply about the technology in this particular talk, just about what we all have to do as an industry, and perhaps give you hope that, in fact, the rather rocky road we've all been on, in the telecom space in particular, is now forking, and perhaps going into some sort of nice superhighway into the future that actually will be better for not just economies, but humankind. So I am going to talk about a concept that we had, and I just frankly borrow ideas from other people, so my job is to listen to smart people and then take the best of the ideas and do something with them. So this idea of creating time is an interesting one, and in fact it's one I borrowed from an economist called Jacques Attali. Some of you may know him. He was a very famous French economist, still alive, so not meaning to suggest that he's otherwise. But he actually had this, he'd gone off to a conference and thought about what he'd heard, and he said, you know what, the fundamental value, the commodity of the future that we need to optimize is time. It's what people don't have enough of, it's what we need to optimize around. I'm going to explore that a little bit more in this talk, and hopefully connect it to the idea of the new networks we have to build, and economic consequence of all that. Okay, so it should be an interesting journey. Let's see if we can do it. So I'm starting with the bad part. This is sort of a plotting of Gordon's. Robert Gordon wrote a book called The Rise and Fall of American Growth. There's rise, there's fall. This is his data. And what he basically shows and posits is that nothing good will ever happen again. It's a little negative. Sort of a bit like a marriage sometimes. No, so what he says is that the first and second industrial revolutions gave rise to this unprecedented era of growth. That P is productivity. Up it goes. Everything coalesces, and there's a massive increase in human productivity. And ever since then, sort of since the 1960s, it's just been a demise. Now, just to be clear, it's all growth. The axis says growth. It's just a decrease in the rate of growth. So we shouldn't be too depressed that we're actually declining. We're just not growing as fast. And he says, in fact, that's it. Look, if you look at the internet age, it's in here. Nothing good, right? So he then says, in fact, he can't see any way out of this. So I'm going to posit there is a way out, and in fact show data that suggests this is true. So P, productivity. Think about productivity. What is it? It's the production of something from an input to an output per unit time. Right, that's it. Goods per unit time. So think about it. If I could actually decrease the amount of time I take to produce something, and productivity goes up. So that's one element of time we're going to explore a bit. But what do you do with that time is the other question. Right? If I've saved time, what do I do with it? Well, that's the other thing we're going to talk about. Because one part of that is people will actually do more creative, cognitive, aesthetic things. So think of that as growing intellectually. But the other thing is, and I've been reading this book by Yuval Harari called Sapiens, he points out that capitalism is founded on the premise of optimism about the future, and in fact, generally that optimism is founded on the ability to go and explore and find new things. When you find those things, you monetize them, and the cycle goes on and on and on. So in fact, there's two elements of time we're going to explore. One is humans need more time, because in fact, we're all becoming overwhelmed, so we're going to invest in platforms that save us time. But at the same time, we're also going to use that time to create new and good, and that's the productivity effect. So I'll come back to that. So, just to put it in context, this is a big deal. Sitting here today, we should all be aware that this is not just any old era. This actually is a technology revolution that we're facing. And I want to talk a little bit about that because you'll understand that they're rare. There've only been 5, actually, in the modern era. The definition of technology revolution, by the way, again, economists define this because I'm not capable of it. But it's actually, there has to be a new technology. That's not really surprising. It's called a technology revolution, after all. New technology, but it has to be networked. That's the other thing. Think of that as a bit of a Metcalfe's law effect. Those of you know who Bob Metcalfe is, smart guy, invented Ethernet. But he had a law that said when the power of a network goes up in proportion to the square of the number of connected things. So you have more connected things, power goes up, utility goes up. So networking a technology together is important, but even that isn't enough. To be a revolution, it has to profoundly change society and economy. That's the definition by economists. So I'm going to say all those criteria are going to be met in the coming era. We know we're at a place where we want to change society. We know from the productivity data we need to change economies. So what we need is a technology and networks that connect those technologies, and then we've got the formula. So let's look back to see which ones we've already lived through as humans. Well, here's the list. I copied it from Wikipedia, so it must be true. So this is it. The first one was called the financial. Actually, it was called the financial agricultural. And what's the technology here? Well, it was actually a financial vehicle, stocks and bonds, and the network there was actually a human network. People got together, traded those things. The next one were 2 industrial revolutions. That was all about steel and rail and engines and ships and planes. Again, it's obvious what the technology is. It's engines, generally. And the network is physical rail and air traffic networks and shipping networks, right? So those are the networks built there. Then comes the so-called scientific revolution, and that was really where we started actually processing signals, not goods, if you think about it. The early networks were moving money and goods. That network was moving bits. Then the internet age. What's that? Another network, this time moving bytes. It's actually very similar to the scientific one. It's just it moved bytes instead of bits. And what do I mean by that? Well, bits, it was mostly control bits that were moving around those early networks. Even telephony, you could argue, is largely control with a bit of voice. But most of those were control networks. The internet was actually a data network. So we started moving data, not just control bits. But otherwise, it's a network moving things around. And then I'm going to argue that the one that's coming, the automation of everything, we're moving knowledge. Right. So we're moving higher up this sort of value stack, and we're going to ship knowledge around. So think of it, it's moving money, moving physical goods, moving bits, moving bytes, moving knowledge. That's what we're about to do, and that's the new age, and we've just got to find the way to do that correctly. Okay? But it's a big deal. There haven't been that many. So, and I'm going to call that broadly, these 2 areas, the 3rd industrial revolution, and this one the 4th. People count differently, you'll hear. But the whole industry 4.0 paradigm, think of it as this, the 3rd one being the scientific and internet age as the 3rd, and so this is the 4th industrial era. It's a big deal. All right, so I want to, first of all, explore this idea of time a little bit, because it's interesting. So remember I said there's a saving of time in terms of productivity, enhancing productivity, but there's also what do you do with that time? And this is a little bit answering that question. This is called Maslow's hierarchy of human need. It's fundamentally what psychologists believe humans want. And what they actually want, he says, is to spend less time at the bottom and more time at the top. So you feel worthwhile if you're transcendent. You've learned things and you're able to teach others, and you feel not so worthwhile if you're spending all your time at the bottom. Now, some of the things at the bottom are actually rather fun. But, yes, you can read too. But some are not so fun. And so his point is you don't want to spend too much time down there, you want to spend time at the top. So it is a time-saving equation. And, of course, since we have a finite amount of time, we have to trade one for the other. So think of it in productivity terms. If I could spend less time doing tasks at the bottom, think of these as relatively mundane tasks, and more time on creative tasks, I can create new, in a capitalistic sense, new knowledge and new wealth. And so that's what I'm going to play with. But let's look at where we are as an industry. Here is what someone pointed out. I showed this a year or so ago. This is where we are. So if you adapted it for the modern era, this is where our industry is. Use free Wi-Fi as a broad description of just internet service, but that's where we are. In fact, we've actually, I would argue, conspired to get ourselves there by actually devaluing ourselves continuously. The trick for our industry is actually to build something that actually has value higher up the stack here. I'm going to show you fundamentally, since networks have to be re-architected, and this is going to be important, where all the value goes has to be more in the network. And it sounds incredible, but hopefully I'll convince you. But that's the problem we have to solve. We have become almost a human right? And we're certainly treated as if we're commoditized and mundane, but we're not valued higher up the stack. Until we solve for that, our industry will always be where it is. But the good news is that's going to change. Okay? So let's explore that time thing, because I could just say it's about time. I could say Jacques Attali said it's about time, and you could believe me. But let's actually see if it's true. So this is the past. I'm going to argue that, in fact, most technology revolutions, in fact, all of them, are premised on time. I said technology and networks. But what's the point of building new technologies and networks? It's not just for fun. It's to save time. So let's look at that. That's one of the early networks. It was a car. If you think about what's the point of a car, it's a way of getting from A to B more efficiently. In fact, if you look at it, it's about 100 times faster than walking today. Back then, it was actually about the speed of walking. Then planes, same, printing press, Hubble Space Telescope. You think, well, what's he talking about, Hubble Space Telescope? Well, what's the alternative to seeing further is to go, right? You actually have to go. So that would be 5,000 times it sort of saves in terms of the fastest rocket we have relative to if we had to go there to see it, so we see further. So all of these are time-saving devices. That's fundamentally what the past has been about, okay? And that saving of time gave rise to that industrial growth. Now, let's do the present, and you'll see the problem. Here's the present. So I'm going to ask you, you have to actually participate at this point. Google, does it save time or waste time? You have to answer, come on. Saves time, I'll give you that. So that's a good one. Facebook, waste time. Amazon, saves time. Apple. See, I normally on Apple people say, because it basically is a distraction as well, right? So to some extent, it's a portal into all the things that you waste time on as well as the things you save time on. So Apple is a bit of but the others, I agree with your answer. Google, actually, access to data, not knowledge, but data. We call it our memory assistant in some ways. That's how at Bell Labs, we talk about Google as being a memory assistant. It's not a brain, it's not a knowledge assistant because it doesn't do those things. It does improve your memory because you can go and discover things you used to know. Facebook's its fundamental problem is it's a distraction, right? We use it to fill time. Now that has value. Up there in Maslow's hierarchy, at the top was cognitive aesthetic things. Now I wouldn't argue it's cognitive aesthetic in the way that we would like it to be, but you can choose to spend time up there, and that's okay. So that it's in that realm. But they realize that their value isn't quite as fundamental as Google. So as they add in more information content, more news services, etc., you get to see that they're really rounding out that value proposition. Amazon, of course, saving time and goods. You find the good you want at the price you want, and generally they optimized for the one part they couldn't control, delivery. Right? When they introduced Prime, they were solving for the part of the time equation they couldn't solve for before, which is getting it to you as fast as, frankly, you could get to a store and back. And then Apple I've commented on. So it turns out, if we look at the past, those other things, the industrial things, everything was saving time. These, it's a bit of a question mark. Right? Some save time, some waste time. So it shouldn't be any surprise that we've paused in the productivity. Because the internet age has not really saved time. It's moved value around, for sure. It's moved value out of our industry into these companies. But I would argue it hasn't really yet created new value. But the good news is there is going to be new value created. Okay? So let's talk about the future. So what is it going to be? What haven't we done that we should have done that would have created new value? Well, it's connect everything. We've connected people, basically, right? And then, of course, some people to media, whether it's a written media or visual media or audio media. That's been connected, so I think that's been digitized well. But we haven't connected people to everything else. Every other process, every other system, every other platform, every piece of our world is not connected, and that's the gap. And when we round out that gap, we'll actually have a complete view of the world we live in and all the systems, processes, and platforms. And when we do that, we can optimize it. So the future is about actually connecting all those things, not just for fun, but actually so that we can then make intelligent decisions, and not alone, because we don't have enough time or mental capacity. We're going to use machines to assist us. But assist us they will, and by assisting us, they will save our time, so we can spend our time doing new creative things that machines can't do. So that's sort of my optimistic treatise about the future. So we're going to connect physical and digital, and we're going to do it to create new knowledge, automate outcomes, new experiences, and save time. So that's the goal of the future. Just to put it in another context, I chose this picture for a reason. When you think about how you think about a new idea, we ask, what's the most common way when you want to brainstorm about something? What do? You either go to a whiteboard or you pick up a paper and pen. So if you think about it, creativity is stuck at the paper and pen. And all these other things, we've increased the performance of, or the productivity, thousands of times. We're still left with human brains and a paper and pen. That's it. So that's what we're trying to actually get to in the future, is optimize that by using machine assistance that allows us to see things we wouldn't otherwise have seen, but then we still make the decision. That's sort of the paradigm for the future. Okay? So I want to convince you that networks play a role. Now, it's a little self-serving, admittedly, but hopefully by talking physics, because I do have that background in sort of physicsy things, I'll convince you that networks have to play a role, not just because I would like them to. So this is easy. It's not going to be painful, trust me. That is a distance, that is time, and I've plotted the speed of light here. So speed of light actually, it turns out it's pretty fast, but not fast enough. So here's the paradox, or the conundrum facing us. We've built networks that essentially have 100 milliseconds of delay. And we did that for good reason, because humans can't process information through their eyes or ears faster than 100 milliseconds. Just the way the brain works. So unless we're changing human brains, which I'm not planning, then 100 milliseconds is processing time for your eyes to see, your ears to hear, brain to process, outcome to happen. So that's why we built networks that were about 100 milliseconds. Okay? So if that's true, and I then take 100 milliseconds and say, how far can light go in 100 milliseconds? It can go a long way. It can go 10,000 kilometers. Okay? 10,000 kilometers is a long way. Now, let's assume there's a set of things that actually you need to do faster than humans can process. And we'll call those IoT things, but I'll indicate that there's another thing that humans actually can do faster than see and hear. So let's say 1 millisecond is our new number, the magic number for latency for, say, industrial control or automation systems or autonomous vehicles. And I'll show you the examples in the next slide. I can only go 100 kilometers. Fundamentally limited by the speed of light. I'm either going to speed light up, which falls in the category of hard, or I'm going to accept that my network and application and analytics and security has to terminate 100 kilometers away from every user. So that's a big shift. Instead of being relatively centralized, we built networks that most of the data processing, think of it as control plane functions and the application function, could sit 10,000 kilometers away and you wouldn't notice. The cloud era has been premised on the fact you didn't notice. That was a long way away in the US a lot of the time. And now it's got to be 100 kilometers away. That means every network has to be re-architected to be city level, roughly, right? Major city level networks where all the action is. And again, just to emphasize, it is not just the data, but it's the analytics function, it's the AI function if you want, it's the expert function of the person who's analyzing that data, it's the security function that's securing it. The whole thing has to be encapsulated there and back within that 100-kilometer radius, okay? And it's all by the speed of light. So now I have to convince you that 1 millisecond is in fact the right number, right? So that's what I'm going to do next. So here's the future, latency versus bandwidth. And this is not every application, I just put some things down here. But this is the latency dimension. You see that basically human communications, basic sensor technologies, you programming your thermostat, and video don't need very low latency because of that perceptual thing I talked about. And the bandwidth is relatively modest, a couple of megabits per second per session. But the future has to be about much lower latency for these control systems, and actually much higher bandwidth. So let me talk about the higher bandwidth. VR, AR, let's start with that one. Or 360 video, in fact, there's two types of things. The 360 video, if I have a 360-degree view of something, it's pretty obvious I need about 20 times as many screens as my current view, because the current view is only 30 degrees. Your field of view, when you look at a TV screen, is about 30 degrees. When you actually have 360, I need about 20 of those. So multiply current bandwidth of video streams. A high-resolution stream might be 6, 7, 8 megabits per second for a 2K or 4K stream. Then I'm going to be up around 100, 200 megabits per second, maybe even 500 megabits per second. That takes me up there. Now, if I also put on a headset and look at it in virtual reality or augmented reality, it turns out my brain has one sensitivity that's faster than 100 milliseconds, and I can do a live demo of this one. It goes like this. I'm going to pick Stephen Carter, since he's my best buddy. So here's Stephen. This is what the brain can do faster than 100 milliseconds. That was it. What I did is I managed to move my head and look at Stephen without ever taking my gaze off Stephen. And you think, well, that's not clever. It's very clever, though, because your eyes should go like this. But in fact, they don't. No matter how much I do this, I still look at Stephen. So your brain actually does an inversion function that takes it about 7 to 10 milliseconds. So when it spots your head moving, and it knows that it wants to stay looking at you, it moves your eyes in the other direction. You think, well, that's not clever. Well, it is clever. 7 milliseconds is a pretty short period of time. The point is when you put on VR goggles and if it doesn't respond in the right way, what do you do? What does your brain do when things are not right? Makes you throw up, exactly. So that's what will happen if you ever put on VR goggles. You don't have a choice in this matter. And someone actually explained to me, again in a sort of sapiens-like way, why would the brain throw up? Well, it doesn't throw up, the stomach throws up. And you think about it, go back to human origin. So it goes back. What would have been the thing that caused your brain to see differently? Poisons. Right? You take something that you eat something you weren't meant to eat. You start getting delirious or a distorted point of view, and so the brain, sort of in evolutionary terms, learned that the best thing to do is throw up. So it's sort of we're living in that world. So if we're living in that world, then we have to have latencies in the networking part of a few milliseconds, a couple of milliseconds, right? Because the whole thing, again, the application processing, the video image rendering, etc., has to be 10 milliseconds. So we go to 1 millisecond, and suddenly we're in this brand new realm. And it turns out the same is true for anything that needs precision control. If I want to, here's another number. I try and make things super simple. If I want to know the location of something accurately, a machine, a system, I have to get updates about where it is. Right? So let's do this. If it moves at a meter per second, right? If something moving at a meter per second, which is about slow walking speed, is about 2 miles an hour. It's a not very athletic walker. So meter per second, if I want to know where it is to a millimeter precision, it has to send me an update every millisecond. Otherwise, I'm guessing. Right? So that's another thing. Precision control, I need millisecond latency if I want to know where something is to millimeter precision. Of course, it's moving faster. I need updates even faster. So that's why all these autonomous things end up being in that category, is because I need to know where they are. So they're reporting where they are, so I can then take action, because the system is not completely autonomous. There's always a human or some other system supervising it. So that's the world we've got to build. And if you think about it, we've been here. This is the world we have built so far, bottom left. We've got to build top left, top right, and bottom right, which is very low latency, very high bandwidth networks. Now, there's a nice little wrinkle here. It turns out that at low latency, you get higher throughputs in networks because of the performance of protocols like TCP, where you don't get to send the next byte of data until you've got acknowledgement for the last. If you get faster acknowledgements, you get more data sent. So in fact, low latency and high bandwidth go hand in hand. So that's the future. But everything I've said says networks have to be built for low latency, ultra high bandwidth, and they're going to be built in this reconstructed way only 100 kilometers away from you, okay? And you see that they'll serve all these new needs, and these are new value paradigms, so you shouldn't be surprised that in there is my argument about new productivity and new value. So the summary of this part, and then I'm going to show you that we're already on a very interesting path, is this. We used to build networks that looked like that. They were connecting people-type devices over access networks, IP networks, to data centers that were relatively centralized. We're going to go to this, highly distributed, Same sort of technologies, but very low latency, very high capacity, massively distributed. And if you look at the dimensionality of change that our industry is going to drive, it's here. So I'm going to go 100 times up in bandwidth. You see that. I'm going to go 100 times down in latency. Those two things are related. I'm going to increase the number of devices by a factor of 100. It's not because of people. They're not going to be 100 times more people. It's going to be 100 times more sensor technologies. And so that's 1 trillion devices. The cost of those devices has to go way down to about $1 from, I hear the new iPhone X is $1,000 or pounds, so that's got to go down by a factor of 1,000. And then the battery life has to go up by, I think that's something like a factor of 365. So that's a very, actually it's 3,000, I guess, 3,600. So that's a large change. Now those last two I'm just going to mention in passing, and then I'll sort of wrap up. Why do those device cost and battery life things matter? The only way to actually solve for that is to put the function of the device actually in the network as well. I can increase battery life if I put fewer components in the device. No matter how much I increase by Moore's law the performance of die in a device, I'm never going to increase it by as much as if I move most of the functionality into a local cloud. And all it is basically a sensor and a radio. So that's one way. And at the same time, that decreases cost, right? If I've only got a sensor and a radio in a device, suddenly devices are only $1. So in fact, the network is going to be playing a role in the future of devices because it's the only way to get to those last two numbers, right? So I want to sort of show you where we are, and I'll make my productivity argument. So this is, I found it on the web. Someone produced it. So I'm going to argue that we are the jumbo jet today. We've done a good job. We're quite nice. We get people from A to B sort of in the digital world quite quickly. But where we're going is we're building a Star Trek world. We're going to go on the USS Enterprise of amazingness. But I want to show you that we're already on the path. So here we go. I decided to look back at Star Trek and see how well have we done. So here we go. There are 5 innovations in Star Trek. And you think, well, if you've done that, then you've done pretty well, right? So we'll go through this. Here is... one of those was the communicator, and I think we beat them, right? We created the smartphone. The communicator, all you could say was sort of beam me up, Scotty, and we can do a lot more with smartphones. So we won on that one. Next is this one. The holodeck. It was a room you went into, and you could actually create any reality you wanted and interact with holographic people and species, and I would say virtual reality and 360-degree video rooms, and now direct holographic projection rooms. Basically, we're at the moment creating the holodeck. Next was the replicator. I think we've sort of beaten that. That could just produce food on demand, and we've actually created 3D printers that actually can produce food, but many, many, many other goods at the same time. And by the way, just get back to that productivity point. Think about 3D printers replacing global manufacturing for lots of little things. Where will that happen? It'll happen locally. It'll happen in that same location 100 kilometers away where you can actually have the good, not only the file sent to that location, but then the good will be created and delivered to you just over the local 100-kilometer network, not over national network. So this shift of sort of global to local isn't just about digital, it's actually about manufacturing. And it's about assembly tasks then, because once I've created lots of little things, someone still has to put them together to create the bigger thing. So all of those jobs and will shift as part of this as well. Okay, the 2 things we haven't done. The transporter. That's hard. That's where you go widdly, 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 and you get transported. But I argue that actually that was the wrong idea. That was the one they got wrong. That's pretty silly to think of doing that. It's very hard to reconstruct humans. But actually what it was about is seeing as if you were there. So if, in fact, we could send complete sensory state, me, you here, over a network to another place where I could perceive it like this, then I've essentially transported myself. So I think the answer is virtual transportation, teleportation, which means that we correctly describe these environments through sensors and physiological stuff and new devices. If I can do that, then I've actually virtually teleported, which is more sensible than this one. And then that's the other one. That one is also in the process of being solved, right? Digital health is about solving that one. The tricorder, the doctor did this. It could diagnose any of your alien diseases and your Klingon lurgy. That's what that one did. And that one is being solved. There's a famous tricorder prize that claims to be able to scan for 20 common diseases, et cetera, et cetera. So that one's in progress as well. So if you sort of summarize, we've solved for 3 of them already, holodeck, replicator, communicator, and we're solving for these. And in fact, digital networks are the way we're going to do this with intelligent systems that diagnose and optimize life. So I'm going to come back to my last slide. I said I would actually put it on some sort of basis. This is a basis that says, what could it mean? So the first data is the Gordon data just replotted as technology diffusion. He argues that all those things came together to create that growth. So there's the growth he showed in 1951. Basically, that's where the tipping point was, where the productivity peak I showed in that early graph happened. It's there. And then everything plateaus after that, and that's the top part. And what we've done is we've looked at the digital equivalent of those technologies, and there's a paper, I won't explain it all. It's frighteningly complicated. It's not complicated at all. It's pretty trivial. What it does is say there's a digital equivalent to all those physical things. If we digitize them and we look at those trends and think of it as things like AI, VR, AR, digital networks, edge clouds, those sort of technologies. And then we plotted where we are and then extrapolated by some diffusion curve mathematics, and this is what we predict. That basically, if we do what we say, digitize everything, build networks that allow that all to be analyzed and automated, we will actually have a second productivity burst somewhere between 2028 and 2033. It's because it's made up, we can't really tell. But it's somewhere there within the next, starting sort of decade from now. You'll see the tipping point. But look here, we're already on the first part of that. If I put where we are today, we're on that first little bump where, you know, in exponential trends, they always say the first part you can't see, right? Because it looks linear and it looks small. But that's where we are, and where we're going a decade from now is that. And in fact, fundamentally, networks are at the core of that, as I hopefully have explained. And that's a big deal. And in fact, someone quantified this in terms of how much growth it could be. It was the prediction was 35% growth in GDP. By these effects, and those are papers that we didn't write, but we believe to be true. So that's a big deal. So finally, if you want to summarize my talk, we're on the path to good and great by building new networks that will essentially transform human existence and save time. Hopefully it was interesting to you all. Thank you very much.